Hello and welcome to the first session on cryptography. In today's session, we're going to be talking about Euler's Totient function. I will be explaining what Euler's Totient function is, and we'll do a couple of examples along the way. So let's go ahead and get started. So we can define Euler's Totient function with the letter phi of n as the number of positive integers less than n and relatively prime to n. Okay? So if we are asked to, for example, find the totient function of a number, say 102, what we're actually asking is to list all of the positive integers that are less than 102 that are relatively prime to 102. So how do we actually, first of all, find those relative primes? So if we take the number 102, for example, we can actually see that it has two factors, 6 and 17, right? And we know that 6 has two factors, 3 and 2, and 17 only has two factors, 1 and 17. So the numbers 3, 2, I should say 1, 2, 3, 6, and 17, those numbers are actually not relatively prime to 102, so they should be excluded. Okay. We can also come up with two other factors of 102, such as the numbers 2 and 51. 51 is not a prime number, again, because it can be expressed as the product of 3 and 17. 2 can be expressed as the product of 1 and 2. So we also see that there are other numbers that are not relatively prime to 102. So those should not be included in the totient function of 102. And we can also try another two possible factors for 102, and that would be 3 and 34. 3 times 34 gives me 102. 34 is not a prime number because you recall a prime number is a number that can only be divided by itself or by 1, but 34 can be expressed as 2 times 17. So what we're going to do is we're going to actually come up with a way to basically find those prime numbers, we call them n, and we'll come up with a formula on how we can compute this. So let's go ahead and take a look at the formula. So we're going to say that if n is prime, we're going to use this totient function, phi of n equals n minus 1. In other words, we take that number and we subtract 1 from it. However, if the number n is a composite number, and what we mean by composite is that it can be expressed as the product of two numbers, we'll just call them p times q, where p and q are primes, then we're going to be using this totient function. Phi of n is equal to p minus 1 times q minus 1. That's the formula that can be used only if n is composite, meaning it can be expressed as a product of two prime numbers. So this would be case number 2. So we'll call this number 1. This would be number 2. We also have a third case, which is probably the most useful one, and that is if n is either prime or composite. Okay, so we're going to be using this formula. Okay, so what does the formula say? It states that the totient function phi of n of any given number is expressed as n, the prime number n, times 1 minus 1 over p sub 1 times 1 minus 1 over p sub 2. And then we continue doing this where p sub 1, p sub 2, etc. are considered distinct primes. Okay, distinct primes, or different. Okay, so what we'll do is we can actually apply this particular formula, case number 3, or formula 3, for the example we did earlier of finding the totient function of 102. So let's go ahead and do this now. So let me first of all rewrite the formula in a more generic way. So phi of n is going to be defined as n times, we can actually use the sum of the product symbol, okay, of the number, however prime number, whichever prime number we'll be using for 102, excuse me, the relative prime numbers of 102 times 1 minus 1 over p. Okay, so this is just a more general statement, similar to the, it's actually a restatement of the function that we did earlier. So let's go ahead and apply this to our example here, which is what is the totient function of 102? Well, that's going to be equal to the number that we're dealing with, 102. And now we can actually say it's going to be multiplied by 1 minus 1 over. The first p that we're going to be using is 2. And then we're going to multiply this by 1 minus. The second p is going to be 3. And we're going to multiply this again by 1 minus. The third p is going to be 17. Okay, so if you wonder why we picked those, we can go back to the previous example, and we notice that we have the 17 repeated. So we know this is going to be the number, or the relative prime. We also see that the numbers 2 and 3 are repeated. Okay, based off of those factors that we did earlier for 102. So by applying these numbers to the formula, and by doing the math, we can see that this is going to give us 102 times 1 minus 1/2 is 1/2, times 1 minus 1/3 is 2/3, times 1 minus 1 over 17 is 16 over 17. Okay, and that's going to be equal to, we just kind of cancel out the 2's, 102 times 16, that's going to be 1,632 divided by 51, and that's going to be 32. So this is the magic number that we're after. What does that 32 mean? It means that we have 32 relative prime numbers to 102. And we can go ahead and list those numbers as follows. So the totient function of 102 can now be listed, or can be defined as the list of these, of 32 numbers. Now those numbers are going to start with 1, 5. Remember, the 2, 3, and 4 are not relative prime numbers to 102, so we're going to exclude those. And 6 is not. So the next number on the list is going to be 7, 11, 13, 19, 23. So you just basically list all the numbers that are not included in the factors that we did earlier. in this slide. Okay, so for the sake of time, I'm just going to go ahead and write them down for you: 21, 31, 35, 37, 41, 43, 47, 49. Next is 53, 55, 59, 61, 65, 67, 71, 73, 77, 79. Then we have 83, 89, 91, 95, almost there, and then 101. So let's make sure that we have 32 numbers in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so it looks like we're missing a bunch of numbers here. So 95, I think the number after it would be 97, and then there's 99. So that should complete the list. Okay, so those are the 32 numbers that would be considered relative prime numbers to 102. Last word here, Euler's totient really has many practical applications in cryptography, and we're going to be actually seeing this in other video segments that I'll be doing. So before we end it, let me do another example that's probably going to be a little bit easier than this one. So let me go ahead and basically perform the Euler function of the number 99. Okay, so remember, the first thing you want to start with is you list the factors of 99. So this one is going to be easy. 99 can be expressed as the product of these two numbers, 3 and 33. 33 is already a prime number. Excuse me, 3 is already a prime number. So, but 33, we can express it as 3 times 11. And obviously 3 is a prime number, and so is 11, right? So this is 1 times 3, and this one is 1 times 11. This one is the same thing, 1 times 3. So right off the bat, I can actually say that the Euler function of 99, okay, is going to be, now here we're going to be using a property, which is the product Euler function. And that is, we can take the totient of the number 3, and we're going to be using the exponentiation property because we see that the 3 is repeated here. And then we're going to multiply this by also the Euler function of the number 11. So this is just a restatement of phi of 99. Okay. So again, this would be the formula for the Euler totient function, just by using the exponentiation property. So let's start with calculating the phi of 3 square. Remember the formula we used earlier. It's going to be 3 is the n, so we're going to say n squared, or 3 squared, times 1 minus 1 over p, where p is, in this case, is just 3. Okay? And that's going to be 9 times 1 minus 1/3, and that's just going to be 9 times 2/3, which is going to be 6. Now we're going to have to do the same thing for the second number, phi of 11. And that's going to be, the n here is 11. There is no exponentiation here, so we're just going to leave it as is, times 1 minus 1 over 11. And that's going to be 11 times 10 over 11, which is going to give us 10. So now we just need to multiply them out. So phi of 99, or phi of 99, is going to be the product of phi of 3 square, which we already computed to be 6, times phi of 11, which we already computed to be 10. So that's going to be 6 times 10, which is going to be 60. So 60 basically tells us that there are 60 relative prime numbers or relative prime numbers to the number 99. And that's how we compute Euler function. So if you enjoyed this, feel free to hit the subscribe button. I'll be adding additional video segments on cryptography in this channel. Have a good day.